In this video, we introduce a motion planning framework called Geometric Manipulability Reinforcement Learning, GMRL. For centuries, the wheel has been an innovative transportation tool. However, when encountering obstacles such as stairs, traditional wheels cannot overcome them and may fall. Transformable wheels, like step, can deal with this issue with high stability and efficiency. However, planning and controlling their transformation accurately and effectively present challenges. From the perspective of system models, the system model changes due to various contact points and dynamics. Consequently, discrete phase modeling is required to employ conventional control knowledge. Reinforcement learning has emerged as a solution due to the relaxation aspect of system modeling. However, the results of reinforcement learning are sometimes unintended and divergent. Therefore, we propose a motion planning framework for transformable robots called GMRL. GMRL is divided into two phases: manipulability estimator and motion planner. The manipulability estimator employs graph neural networks to learn dynamic manipulability and estimate undefined values. To estimate the next actions, we need to understand the relationship between two shapes. A graph structure is convenient for expressing relationships in a non-Euclidean space. Although the three graphs may appear different in an Euclidean space, they have the same structure in a non-Euclidean space, because the connections of each node are equal. In this paper, the points in the graph structure are nodes that describe the various shapes of the transformable wheel. The relationships between nodes, called edges in the graph, denote the variation of dynamic manipulability. Dynamic manipulability can be calculated from the composition of kinematics and dynamics. In this paper, we employ the inverse of dynamic manipulability condition number between two transformations. Based on the dynamic manipulability graphs, GNN learns the variations of dynamic manipulability to predict edges. If a new node comes through GNN, it can estimate edges from the node and the other nodes, and extract the maximum measure as the next action. Because a higher measure indicates that the transformation to the shape is easier in the current situation. The motion planner accepts action guidelines from the manipulability estimator with an activation ratio alpha. The activation ratio ensures the robustness of exploration and effective convergence from the guidelines. During training, the robot simulator updates a plan policy based on the compound of actions. The motion planner assumes that the manipulability estimator is pre-trained. If the action guideline or action from the policy enters the simulator, reinforcement learning calculates the reward for updating. The reward function considers transformation energy and wheel position. After reward calculation ends, RL updates policies, and the overall sequence repeats until the training is completed. To demonstrate the effectiveness of GMRL, we conduct simulation experiments using the MuJoCo simulator. As shown in the above videos, GMRL generates the most stable motion plan, compared to the experiments of dynamic manipulability and reinforcement learning individually. GMRL can generate robust motion plans through regulating the dynamic estimator activation ratio, alpha. As shown in the above videos, alpha determines the bias between dynamic manipulability and reinforcement learning. The generated motion plans can be expressed as the graph above. The optimal alpha in this paper is 0.5. In terms of dynamic manipulability measure, a ratio of 0.7 appears to be much better. However, the optimal transformation shapes considering transform efficiency are at a 0.5 ratio. This demonstrates that combining two strategies properly can generate an optimal and robust motion plan. That is, GMRL.